this telescope that is now going to take us back in time. It's a time machine. It's going to take us back to the very beginnings of the universe.
The Big Bang is the defining narrative of modern cosmology, a bold declaration that our universe had a beginning and has a finite age, just like the humans who live within it. That finite age, in turn, is defined by the evidence that universe is expanding. Again, and unfortunately, many of us are familiar with that feeling as well. Those two ideas, a singular cosmic beginning followed by billions of years of cosmic growth, are so strange that some people have never made peace with them. As a result, skeptics have been questioning the validity of the Big Bang model for as long as there has been a Big Bang model. And as NASA's $10 billion time machine, James Webb Space Telescope, launched, it gives us the perfect time to go back in time to the beginnings of the universe. The most powerful space telescope imaged very old, large, well-formed galaxies that defy current universe models. Join us as we dig into how James Webb Telescope might shatter the Big Bang Theory. As humans learn more about the cosmos, we find that the more we know, the more questions arise. And perhaps the most important question about the universe for much of the 20th century was whether it had a beginning or if it has always been this way. For the British cosmologist Fred Hoyle and other believers in the latter steady-state theory, the compelling logic was simplicity, said Jay Gallagher, an astronomer and professor emeritus at the University of Wisconsin-Madison. That at one point something changed and the universe created matter. Why did that have to be? Hoyle, the steady-state proponent, attributed his rival's beliefs in the Big Bang, as he dubbed it, to the influence of the Book of Genesis. Then came a hiss in a radio antenna at Bell Labs in New Jersey in 1964. The hiss was generated by microwaves arriving from everywhere in the sky, exactly as predicted by the Big Bang Theory. The light was released in an early phase transition as the hot, dense universe cooled. The discovery of the cosmic microwave background, as it was called, did not immediately end the debate. Steady-state folks like Hoyle distrusted its interpretation and clung to their theory for many more decades. But for others who recognized the afterglow of the Big Bang when they saw it, the CMB created a puzzle. The near-perfect uniformity of microwaves coming from all parts of the sky indicated that the newborn universe was astonishingly smooth, a puree of matter. The puzzle is, we see a very lumpy universe today, said Faber, who was a graduate student studying galaxies in the late 60s. So the first challenge in understanding galaxies is to understand how the universe goes from smooth to lumpy. Cosmologists knew atoms must have gradually clumped together because of gravity, eventually fracturing into structures like stars and galaxies. But on paper, it seemed that the growth of structure would have been extraordinarily slow. Not only was matter initially smoothly distributed and thus pulled in no particular direction by gravity, but the expansion of space and the pressure created by light itself would both have worked to separate matter, counteracting its weak gravitational attraction. Enter dark matter. In the 1970s, Vera Rubin of the Carnegie Institute of Washington observed that the outskirts of galaxies rotate much faster than expected, as if whipped around by some extra invisible source of gravity. This evidence for substantial missing matter in and around galaxies, dubbed dark matter, matched Fritz Zwick's 1930s observations that galaxies seem to attract each other more than they should based on their luminous matter alone. Also in the 70s, Jim Peebles and Jerry Oestreicher of Princeton University calculated that rotating galactic disks consisting only of stars, gas, and dust should become unstable and swell into spheres. They posited that invisible matter must be creating a stronger gravitational well within which the visible disk rotates. In 1979, Faber and Gallagher wrote an influential paper compiling all the evidence for dark matter, which they pegged at about 90% of the matter in the universe. The current estimate is about 85%. These researchers realized that dark matter, with its substantial gravity and imperviousness to light's pressure, could have bunched up relatively quickly in the early universe. Peebles, who won half of the 2019 Nobel Prize in Physics for his contributions to cosmology, developed a qualitative picture in which dark matter particles would have glommed together into clumps, known as halos, that then combined into bigger and bigger clumps. The British astrophysicist Simon White demonstrated this hierarchical clustering process in primitive 1980s computer simulations. Though visible matter was at that time too complicated to simulate, researchers surmised that the conglomerating dark matter would have brought luminous matter along for the ride. Corralled within dark matter halos, atoms would have bumped together, heated up, sunk toward the center, and eventually gravitationally collapsed into stars and disk-shaped galaxies. Although most cosmologists became convinced of this picture, a big question was how variations in the density of matter initially set in, jump-starting the gravitational clustering process. Spectacular realization, the cosmologist Alan Guth scrawled in his notebook in 1979. He had calculated that if space suddenly blew up like the surface of a balloon at the start of the Big Bang, this would explain how it got so huge, smooth, and flat. Cosmic inflation, as Guth dubbed the primordial growth spurt, quickly became popular as a Big Bang add-on. Cosmologists soon noted that during inflation, quantum fluctuations in the fabric of space would have gotten frozen in as space blew up, producing subtle density variations throughout the universe. The putative dense spots created by inflation could have served as the seeds of future structures. These tiny density variations were indeed measured in the CMB in the early 1990s, the feat that earned John Mather, the Webb telescope's top scientist, his Nobel. But even before they were measured, people like Faber were working the dense spots into the plot. In 1984, she and 3 co-authors published a paper in Nature that strung everything together. It's the first soup-to-nuts description of how inflation can make fluctuations and what the fluctuations would do later to make galaxies, she said. But the story was speculative from start to finish, and even if it was broadly true, key dates and details were unknown. In 1993, the Space Shuttle docked with Hubble, and astronauts installed a sort of contact lens. And then, a new revolution in astronomy and cosmology took place. With the Hubble Space Telescope, we've learned that stars, galaxies, and supermassive black holes existed far earlier in cosmic history than anyone expected, and that they have since undergone radical change. We've learned that dark matter and dark energy sculpt the cosmos. With the Kepler telescope and others, we've seen that all manner of planets decorate galaxies like baubles on Christmas trees, including billions of potentially habitable worlds in our Milky Way alone. These discoveries have raised questions that only their successor, the James Webb Space Telescope, can address. The James Webb Space Telescope can look further back in time than any other telescope, observing distant stars and galaxies as they appeared 13.5 billion years ago, not long after the beginning of the universe as we know it. How is this possible? How can a machine look back in time? It's not magic, it's just the nature of light. Telescopes can be time machines. Looking out in space, is like looking back in time, NASA scientists explained on webbtelescope.org. It sounds magical, but it's actually very simple. Light needs time to travel across the vast distances of space to reach us. All of the light you see, from the twinkling of distant stars to the glow from your desk lamp a few feet away, takes time to reach your eyes. Luckily, light moves staggeringly fast, roughly 670 million miles per hour, or 1 billion kilometers per hour. So you'll never notice it traveling from, say, the desk lamp to your eyes. However, when you're looking at objects that are millions or billions of miles away, as most objects in the night sky are, you're seeing light that has traveled a long, long way to reach you. Take the sun, for example. Earth's home star sits an average of 93 million miles, or 150 million kilometers, away. That means it takes light about 8 minutes, 20 seconds to travel from the sun to Earth. So, when you look at the sun, although you should never look directly at the sun, you're seeing it as it appeared more than 8 minutes ago, not as it appears right now. In other words, you're looking 8 minutes into the past. The speed of light is so important to astronomy that scientists prefer to use light years rather than miles or kilometers to measure great distances in space. 1 light year is the distance that light can travel in 1 year, roughly 5.88 trillion miles, or 9.46 trillion kilometers. For example, the North Star, Polaris, sits about 323 light years from Earth. Whenever you see this star, you're seeing light that's more than 300 years old. So you don't even need a fancy telescope to see back in time. You can do it with your own naked eyes. But to look truly far into the past, say back to the beginning of the universe, astronomers need telescopes like JWST. Not only can JWST zoom in on distant galaxies to observe visible light coming from many millions of light years away, but it can also pick up wavelengths of light that are invisible to human eyes, such as infrared waves. Many things, including humans, emit heat as infrared energy. This energy can't be seen with the naked eye. But when infrared waves are viewed with the right equipment, they can reveal some of the hardest to find objects in the universe. Because infrared radiation has a much longer wavelength than visible light does, it can pass through dense, dusty regions of space without being scattered or absorbed, according to NASA. Many stars and galaxies that are too far, faint, or obscured to see as visible light emit heat energy that can be detected as infrared radiation. This is one of JWST's handiest tricks. Using its infrared sensing instruments, the telescope can peer past dusty regions of space to study light that was emitted more than 13 billion years ago by the most ancient stars and galaxies in the universe. That's how JWST took its famous deep field image, and that's how it will attempt to look even further back in time, to the first few hundred million years after the Big Bang. The stars that the telescope reveal may actually be long dead today, but as their ancient light makes the lengthy journey across the universe, JWST treats our mortal eyes to a one-of-a-kind time travel display. After more than a year in space, the Webb telescope has clapped eyes on the most ancient galaxies ever observed. Very shortly after the JWST data became accessible, several claims have been made of galaxies that existed 400 million and 325 million years after the universe began. 2 other groups claimed an even older galaxy, which could have existed 225 million years after the Big Bang, and a third group is claiming to have observed a galaxy that was formed at the staggeringly early time of 180 million years after the Big Bang. That's where the trouble comes in. Current theory suggests that the most ancient galaxies should be very small. Furthermore, they should be irregularly shaped. Over time, these tiny galaxies would slowly merge, eventually becoming much larger, like our own Milky Way. However, these infrared visible galaxies seem to be far larger and more regularly shaped than what was predicted. And this fact has resulted in some commentary, especially from people with a long hostility to the idea of the Big Bang. One article cites a scholarly paper on the topic, whose title begins with the provocative word panic. One such individual is Eric Lerner, who penned the book The Big Bang Never Happened. Others who endorse either creationism or intelligent design are also using these reports to claim the same thing. So, is the Big Bang in trouble? The short answer is no, or at least it's extremely unlikely. But what could be an explanation that doesn't require anyone to rewrite physics textbooks? Well, one simple possibility is that there is dust between the distant galaxy and the JWST. As anyone who has watched a breathtaking sunset knows, dust preferentially scatters away blue light and lets red pass through. Perhaps the reports of distant galaxies are due to their light having shifted toward the red and infrared, not only because of the expansion of the universe, but also because of intervening dust. Another very simple possibility is that because the JWST has only been operating for a very short time, its online optics and electronics have not yet been properly calibrated. It could be that additional operational experience will lead the JWST technical staff to adjust the signal processing and algorithms, which could mean that these early claims could disappear. Of course, it is also possible that the reports are true, and it turns out that early galaxies are larger and better formed than current theory predicts. However, this doesn't have anything to do with disproving the Big Bang. Instead, it may require us to modify theories of how matter in the early universe assembled into galaxies. This would require some tweaking, but that's a far cry from rejecting the Big Bang entirely. So, how will the situation be resolved? Time and more data. These early reports use a simple algorithm involving a series of optical filters to determine the color of light from early galaxies. However, the JWST has more precise spectrometers, which will allow astronomers to get more accurate determinations of the wavelengths of light emitted by these distant galaxies. These better measurements will answer the question. Everyone wants to know what secrets JWST will reveal about the universe, but reliable science takes time. So just wait and see. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. As always, thanks for watching, and we will see you next time.